No. Yes, good evening, everyone. Welcome back. Good evening, sir.
Hello.
Yes, sir. Audible, sir.
Yeah, you are audible myself.
Great, sir. Great, sir.
Yeah,
So I'll pass the control to you, sir.
yeah, please. So it's raining, so it's cold here, so that's why I'm wearing
Great.
this sweater. Don't
Great,
mind.
sir. Great, sir. Great, sir.
Yeah,
So, dear students, okay, for all of you, that's information. So, sir is Dr. Srihari. So, he did PhD at IIT Madras. So, he's always our favorite faculty for SS and communication.
yeah,
So, he's continuing from the last year.
yeah.
And
For
it
your
was a
information, myself and Kumaran sir are colleagues. So when he was doing MTech, I was doing PhD there. Yeah. So it's a
yeah,
friendship goes back to
from
early.
there it was a good experience
Yeah,
for both of us. So we taught almost all the institutes throughout India together.
yeah.
Good, good,
Correct.
sir. So control is yours. You can. I'll
Yeah.
pause
So
the
I can
control.
share my screen, right?
Yeah, 1 minute, sir. I'll pause the control. It will
Okay.
ask you to accept, and then you can share your screen, sir. I'm making you as a
Okay.
host, sir, right now.
Yeah, please. Yeah. Okay. So let me share. Yes. And screen two. Yeah. Is it fine?
Yeah, sir.
Okay. So we'll start.
Yeah, sir. You can take the control. Yes.
Yeah. So good evening, students. As Kumaran sir has said, my name is Srihari and I work in a company called Continental Automotive, wherein my area of research is autonomous cars. Okay. I work in radar signal processing and tracking and all that. Okay, so that's just a brief introduction of myself. So let's move on to the topic. So signals and systems is very crucial subject in gate as well as your future also. One second, let me, yeah, do that. Pen. Okay, yes, yeah. So this is crucial for all the circuit branches. So what I mean by is For ECE students, you get around 10 marks on average. And for electrical students, you get around 8 marks. This is average score, okay? Not that every time you get so much. Okay, and then for instrumentation students, you get it for 6 to 8 marks. Okay, so definitely each mark counts, and hence you cannot miss this subject in future also. So it will be very useful. For example, for ECE students, it will be useful for communications, and for electrical students, if you want to understand the harmonics in power systems and all that, it's always good to know the fundamentals of signals and systems. And instrumentation, anyway, you require this. So if you want to have anything, if you want to, for example, so I was a COVID patient, so I was yeah, so 2 weeks back I was a COVID patient, and that pulse oximeter, so definitely there are a lot of signals involved, right? So how it measures the oxygen saturation, it's nice. So it all comes in signals and systems. So that is live example of that. But yes, so that you will see in future when you go to companies and do some research, you will understand all that stuff. Okay, so as I said, signals and systems is very crucial, and so this is the average number of marks you get for gate in each branch. So with that warning lessons, you can, what is the warning? You cannot discard the subject. Okay, so, and it's very beautiful subject, and please, if you pay attention to my class, you will really understand how beautiful this subject is. Okay, so I hope that I'll make you understand the fundamental concepts, and I assume that you don't know anything. Okay, I start the subject in assuming that you don't know anything, so forgive me for that. Okay, so you know that, but still, so as far as I start the course, I assume that you don't know anything, so it will be a fresh start for you, even if you have not studied this. So if you attend my classes, you will definitely, and I am hoping that you will definitely understand this topic. Okay, so the textbooks which I follow for this are, so the title would be Signals and Systems. Okay, so forgive me for my handwriting. So tell me if you don't understand the uh, words, whatever I am writing. So this is the title of the textbook. You should be aware that this is a Bible. So authors are Oppenheim, Wilski, and Nawab. Okay. So second edition is available. It's 90, second edition came in 96. Still, it's a great book. Okay, and the same title, but the authors are different. Simon Hacking. So he is also a very famous guy, Simon Hacking, and Van Veen, Barry Van Veen. Okay. So this book, third edition, is available in the market. This is also a good book. So if you want to start fresh in this course, so I prefer this textbook. Okay, yes, and the same title Shom series is there, that is also very good. So if why I prefer this textbook as far as gate is concerned, because it's concise and it's very nice. So all topics are covered in this textbook, and it's like a small textbook, some 250 pages, and complete topics are covered in this, and lot of problems are solved, lot of unsolved problems also are there. So it will is a good book. So you can, as far as gate is concerned, you can buy this textbook. And if you want to understand the subject very nicely from scratch, I prefer this textbook. And yes, so after reading these two textbooks, so if you are fascinated with signals and systems, then you can go for this textbook. Okay, so all these things, and these are the books which should stay in your library, in your personal library. Okay, right.
A
So
small interruption, sir. A
yeah,
small interruption, sir. Please admit the students in
where
the
are
waiting.
they?
Waiting.
Where is that?
Admit all. It may be showing admit all
Uh,
students in waiting. See waiting room.
Waiting room. Okay, one second.
It will pop up, sir. In front window, it will pop up in front of the screen. Maybe some students are in waiting room.
Okay.
Able to see, sir?
No, no. 11, 11 entered the waiting room.
Okay. Then
Okay.
admit all, sir.
Where is that? Admit all. I don't see that.
There itself. If you click the see waiting room, then it will show.
Where is the waiting room?
Okay. 1 minute, sir. Let me 1 minute, sir. Stay
Yeah.
online.
Yeah, please.
Sandesh, நீங்க join பண்ணுங்க. getting
Ash.
joining, sir. They're trying to join, it will show as admit. Or if more than one is waiting, it will ask for admit all.
Okay, I am not seeing that.
Okay.
13 people entered the waiting room. That's what I
Yes,
got
sir.
here.
That you click that, sir.
Yes, okay. My God, power gone.
Okay.
Still in net will be there for a while. We'll see.
Okay. Okay.
So don't get scared, yeah. My eyes are there.
So you can admit them. Admitted, sir. Everyone. Yes, almost, sir. They joined.
They
So
joined. So I didn't do
yes.
anything actually.
Okay. Okay.
Yeah. So let the power come.
Uh, okay. Uh, Not yet joined.
Yep.
Not yet joined.
Yeah.
See the waiting room and admit them, sir.
Waiting room. I didn't see here.
In front top. You
Top.
said around waiting room 13 are there, something like that. You said
No, no. They already are inside. That's what it was telling.
that is 17.
Yeah.
Total participants is
Participants
17.
30. Total participant is 30.
Yes, that waiting room is not yet allowed. It has to be admitted. That
Here
is
I don't.
including waiting room list, sir. In
Okay.
participant window, you just open the participant window. There
One
you can see
second.
the waiting room list.
Participants. I opened.
In the top, you can move the cursor to the top. There you can see admit all.
Oh, okay. Wait. Admit all. Yes. Yes.
Admit all.
Yes.
Yes, sir.
Yes. Sorry. Sorry.
No problem, sir.
Now, first time I'm using this
Yes,
Zoom.
yes.
So yeah.
So next day things will be much better.
Yeah. Yeah.
Done, sir.
Correct.
Everyone joined. Everyone
Joined. Ah.
joined.
Okay. So hello all again.
Yes, sir. Often, sometimes they will lose the internet connection. So
Uh-huh.
when they try to join, it will ask you for admit.
Okay. And I'm not getting that pop-up. That's the thing.
Okay,
So maybe I
okay.
will now and then search that.
Yes, yes.
I'll go up and do that. Yeah. Yeah. Got it now.
Fine, sir. Fine, sir. Fine, sir. Yes.
Yeah. Thanks. Yeah. So shall I continue?
Yeah, please, sir. Please, sir.
Yes. Okay. Yeah. So as I said, these are the three good textbooks, and as far as Gate is concerned, I prefer the last one. And yes, so if you want to explore more, you can read. The second book is actually, yeah, I admit, yes. So second book is actually good in the sense it has a lot of theory also, a lot of problems also. This book is also good, but it looks so bulky and it looks scary. Okay, so but that is also really a good textbook. So I cover material from these three textbooks. But if you want to buy a good textbook, you go for this one. Sham series book is there. Okay, so with that in mind, let's move on to the topics. So what are the chapters we are going to see? So first chapter, we will talk about introduction. It's a big chapter. We will see a lot of topics, so don't miss this. Okay, so I mean, don't miss any chapter. Yeah, but yes, okay. Yes, so first chapter would be introduction, and I'll take some time here. So maybe 6 to 8 hours. Okay. Yes. So next second chapter is linear time invariant systems. Okay, this is very important chapter. This is the crux of this complete signals and systems. Okay, here we talk about what is called uh, convolution, correlation, all those topics will come. So I'll make you understand what actually convolutions are and all that stuff. Okay, so next we talk about continuous time Fourier series. That is the third chapter. First we will finish the continuous part. Okay, continuous time part. So that's why next let's move on. We will move to continuous time Fourier transform. Then we talk about Laplace transform. Then we talk about, so with this we are done with the continuous part. So next we talk about what is called the discrete time Fourier transform, and next we talk about the Z transform. That is the seventh chapter. Next we talk about what is called discrete Fourier series and also discrete Fourier transform, in which we cover FFT and all that. Okay, so up to eighth chapter, up to seventh chapter is there for electrical students, and DFS. Okay, up to DFS. So first seven chapters, and in eighth chapter just DFS for electrical students. Okay, and for ECE and instrumentation students, complete 8 chapters are there, and ninth chapter is filter design, and this was there for ECE students also up to last year. So but for 2021 filter design is not there for ECE students. Okay, so we filter design, yes, it is there for instrumentation students. So for instrumentation students, all 9 chapters are there. For ECE students, up to 8 chapters, and for electrical students, up to eighth chapter, first topic, which is discrete Fourier series. Okay, so that is the way how the lecture flow goes. So first we'll talk about introduction. So as I said, I'll take some 6 to 8 hours to understand this. It's a big chapter. So 6 to 8 hours and LTA system. Okay, sorry. Power came again. Yes. So LTA systems will take around 6 hours and so on. Okay. So and we will see for every chapter we'll see last 5 years of old gate questions. We'll solve problems and also we'll solve old gate questions. Okay, so in that way, the how do I teach it? So every chapter I'll finish the theoretical part. While teaching theory, I'll solve few problems, and after finishing the chapter also we will solve few problems, and later we will see last 5 years of old gate questions. So that is the way how the lecture goes for each chapter. For every chapter, theory will be there. While teaching theory, we will solve few problems, and after finishing the chapter, again we will solve the complete list of problems from that chapter, and then we will see last 5 years of old gate questions. Okay, so that is these are the chapters which we are going to see in signals and systems. Okay, so yes, so now let's move on to the first chapter, which is introduction. Okay, so in introduction we will start with the definition of a signal. So how do you define a signal here? How do you define a signal? So signal is, it is a function. Okay, so which varies with respect to one or more independent variables. Okay, one or more independent variables. That is the way how we define a signal. So for example, temperature. So if you want to measure the temperature in a day, so every minute if you want to measure, so you look at the thermometer, you try to measure the temperature. So definitely what is happening, temperature is varying with respect to what, the independent variable, time. Okay, and also the speech signal, whatever I am speaking, if you connect the output of this mic to an oscillator, you will see a waveform. So that also varies with respect to time, so which is the independent variable. So if a function varies with respect to one or more independent variables, then we call that function as a signal. And what should it do? It should convey some information. So or else we call it as a mathematical function, and if it conveys some information, we call that fellow as a signal. So what is a signal? A signal is a function which varies with respect to one or more independent variables and conveys some information. What information it conveys, it depends upon the signal. Okay, it depends upon the signal. So but what actually, then we talk about what is called dimension of a signal. Okay, so dimension of a signal. So how do we define the dimension of a signal? The number of independent variables. Independent variables. So number of independent variables, we call it as what? Dimension of the signal. Okay, so the number of independent variables, we call it as dimension of a signal. So for example, so you have a function like this, x of t. So how many variables this fellow has here? How many variables this fellow has? It has two variables. So what is that? One is time. This fellow is independent variable, and x, this fellow is what? This is a dependent variable. So x of t is a function which varies with respect to one independent variable. And what is that independent variable? T. Okay, and this x depends on t, and hence that's why we call it as x as a dependent variable and t as a independent variable. So what is the dimension of this signal? Because it depends only upon one independent variable, this fellow's dimension is 1. Okay, so dimension is 1. So it's a one dimension signal. But to plot x of t, how many axes you require? You require two axes. Why? So for example, you want to plot a signal. It looks like this, correct? So this is t and this is our x of t. So to plot x of t, some function like this. One second. Yes, so we have a time axis. This is our x of t, and it looks like this, right? So, but this is a one dimension signal, but to plot a one dimension signal, we require two axes. So what are the real time examples of one dimension signal here? So many are there. Just now I said, what is that? Speech. And mathematical examples, so many are there. So for example, x of t equal to t, correct? So that is a one dimension signal, and x of t equal to 1 plus t square. This is also what dimension signal? One dimension. Why? It depends only upon one independent variable t. So like that we can have infinite number of examples, and one of the real time example is speech. Okay, so for and we will, this is, let us say this is one of the example, one dimension signal. And second one, for example, I have a function like this, f of x comma y. What about, let's say this is x square y cube. What is this function here? How many dimensions this function or signal? As far as our signals and systems is concerned, function or signal both are, we can use any one of them. Okay, but in real time, signal means it should convey some information. But yes, so we do little bit of abuse here. Okay, even this we mathematically we should call it as a function, but in our subject we call it as a signal also. Okay, so this signal or function, it is how, what is the dimension of this function here? It is 2. Why? It depends upon two independent variables x and y, correct? So it depends upon two independent variables x and y, and hence this is a two dimension signal. So this is a 2D signal. Okay, to plot this, how many axes you want? You want three axes, correct? And for example, how do you plot that? This is our x, this is our y, and this f of x comma y will come here, f of x comma y, correct? So to plot a two dimension signal, you require three axes. To plot one dimension signal, you require two axes, and so on. So like this we can have again infinite number of examples, right? So x plus y, root of xy, like that we can have infinite number of examples. And what is a real time example here? It's a video, right? So not video, image, correct? So image is an example of two dimension signal. So real time example of a two dimension signal. Why? So usually how does the image look? So I'll draw here itself. So I have an image here like this, correct? So this is an image. So in image, this is our x-axis. So axis will change, but that's okay. Mathematically, usually we draw like this, right? So our x and y axis will be like this. But for in image processing, we take this as x-axis and this as y-axis. That's okay. But how many independent variables are there? Two independent variables are there. Okay, and hence image is an example of a two dimension signal or two dimension function. Okay, and in a okay, yes. Next, let me talk about a three dimension signal like f of x comma y comma z, correct? So this again x y z plus, you can have x square y cube z square. Okay, so this is again what dimension signal, because there are three independent variables. So definitely it is a three dimension signal. So to plot this, how many axes you want? Four axes. So our plane is a two-dimensional plane, so we cannot plot a four-dimensional function in a two-dimensional plane. So yes, you can just vaguely imagine. So you require three axes, and then you have a fourth axis where you have the function. Okay, and for what is the real time, as I said again, you can have infinite number of examples. So what is a real time example? A movie, right? So a movie or video, I say a video is an example of a three-dimensional signal. Why? In movie, what are the variables we have? So pixel values will change, and hence you have f of x comma y, and they vary with respect to time. So our movie we can write mathematically, movie or a video, we can write mathematically as f of x comma y comma t. Okay, right. So in a similar fashion, we have a four-dimension signal. Let's say f of x, comma y, comma z, comma w. Okay, so again we can have x square plus yz plus w cube. Okay, yes, so definitely this function depends on four independent variables, and hence this is an example of a four-dimensional signal or four-dimensional function. And again, infinite number of examples are possible, but what is the real-time example for four-dimensional signal yet? So one is a 3D movie, correct? 3D movie is an example. So how do you represent this 3D movie? F of x comma y comma three dimension, right? So we have x-axis, we have y-axis, and z-axis also will be there, and that movie varies with respect to time, and hence uh, yes, that movie varies with respect to time. So hence 3D movie is an example of four dimension signals. Why four dimension signal? Why it has that varies with respect to x, y, z, and t. Okay, and one more example, electromagnetic wave, right? So electromagnetic wave. So this also can be written as some function of what? X comma y comma z comma. So in that way, we have a multi-dimensional signal. So like that, we can have n dimension signals also. Mathematicians are crazy, so they can have multiple dimension signals. So but as far as signals and systems is concerned, we will talk only about one dimension signals. Okay, in signals and systems we deal, okay, so we deal with only up to gate. Okay, only 1D signals means how many independent variables are there? Only one independent variable. And because we are electrical or electrical engineers, so definitely for us the independent variable is time. Okay, for us the independent variable is time. Okay, yes, so I just wanted to tell you that because the number of dimensions starts increasing, the complexity of the image complexity or computational complexity of processing these signals also would be large. Okay, so for example, I just wanted to give an example. So if you have seen Avatar movie, right? So that is a three-dimensional or four-dimensional signal. So because it is a four-dimensional signal, processing of that image will take a lot of time. Okay, and it's very, very complex. So Avatar movie, each frame, okay, so each frame is 4 GB. Okay, each frame is 4 GB, and what is the frame rate? 60 frames per second. Okay, so it is for each frame, one image is 4 GB of size. And what is the frame rate they have used? The James Cameron, so that camera is 60 frames per second. So the movie is almost like 2.5 hours. So just think how much amount of memory is required. So they talked about RAM itself is like some terabytes. Okay, RAM itself is terabyte, and full image, full video, so full movie is around petabytes. Okay, so that's what I want to say. If the number of dimensions starts increasing, the complexity, computational complexity of processing these signals also increases. So luckily in gate we have only one dimension signal, so you need not worry about computational complexity. Okay, right. So yes, so and also what I want to mention is that so we will be dealing, so this is very important, so we deal only with one dimension signal, and we deal again only with single valued signal. So that also I want to mention. So we deal with only single valued signal. What do I mean by that? The signal takes, okay, so signal takes only one value at a given time. Okay, one value at a given time. So I'll just mention that what it is. Okay, I'll show that within example. Okay, so for example, you have a signal like this, x of t is equal to cos t. So is it a single valued signal? Yes. Why? Because if you plot this signal, how does it look? It's a cosinusoidal signal. It looks something like this, correct? and it's an eternal signal. It goes from minus infinity to infinity. You pick up any time. So let us say this t naught. So what is the value of this signal at t naught here? Maximum value is how much? 1. So at any given time, it can take only one value, and hence we call this signal as what? Single valued signal. Okay, so you pick up any time. So let us say you pick up this time. So at, let's say t1. So at the t1 it can take only one value, and hence we call this signal or function as what? Single valued signal. Now mathematicians, as I said, they are crazy. They can have any types of signal. So for example, you have a function like this, something like this. Okay, mathematicians, you can have cycloid or whatever. So for this kind of signal, for example, you take some t naught. So at t naught, how many values it has there? It has multiple values, right? And we call these signals as what? Multi-valued signals. So we don't deal with multi-valued signals in our course of signals and systems. So we will deal only with what? Single valued signals. So these kind of signals, cos t, t square, e power t, and so on. All those are single valued signals. Means what? At any given time, it can take only one value. Okay, at any given, at different times it can take same value, correct? So at t naught and let us say at t2, all values are one. That's not a problem. But at a given time, it should take only one value. So we call those kind of signals as what? Single valued signals. So in signals and systems, we deal only with one dimension signal and single valued signals. Okay, so we don't deal with this kind of signals. They are crazy. Okay, we don't deal with this kind of signals. So with that, uh, let's move on to the main topic, which is classification of signals. So I just as a recollection. So what is a signal? Signal is a function which varies with respect to one or more independent variables, and it should carry some information. And we have seen the definition of a dimension of a signal, and we have seen few examples for them. And in our course, we will be dealing only with what? We'll be dealing only with one dimension signal and also single valued signals. Okay, we will be dealing only with one dimension signal and single valued signal. So with that, let's move on to what is called the first topic in first chapter, which is classification of signals. Okay, so classification of signals. That is, we will see multiple subtopics in this. Okay, so first one, which is simple, we talk about what is called continuous time and discrete time signals. First classification is continuous time and discrete time signals. So how do you define a continuous time signal? So we define a continuous time signal as x of t. Okay, so we can use x of t, f of t, g of t, whatever. Usually we will use x of t. Depending upon the context, we can change the corresponding function. Okay, so what is the values t can take? So t can, because we say it is a continuous time. So what is continuous? Time is continuous, and hence t can take what values here? It can take any real values. Okay, from where to where? From minus infinity to plus infinity. It's a continuum of numbers, excluding minus infinity to excluding minus infinity and plus infinity. Why? Those two are not, they don't belong to real numbers. Okay, that's why we put this parenthesis. We are not putting square bracket, but we are putting parenthesis. Okay, and what are the values our signal can take? Signal means what? Time or amplitude. If I say signal, just I say signal, so it is time or amplitude? It's not time. Okay, it is amplitude of the signal. Once I say signal, definitely independent variable, we are not concerned. Why? We already know that default it is time, so we need not worry about that. So if I say a signal, definitely we are talking about what? Default, the amplitude of the signal. Okay, if I say signal, so we are talking about amplitude of the signal. So what values amplitude of the signal can take? It can take real values, it can take imaginary values, it can take even complex values. So for example, so I have x of t equal to, let's say, t square. What is this signal here? X of t equal to t square. So t is always what? Real number. So square of any real number is always real, and hence we call this signal as what? Real signal. Okay, means what? Amplitude of the signal is real. So this is a real signal. It's not, you should understand, real time signal is different, real signal is different. Real time signal means what? All the natural signals, whatever you see in nature, like speech signal and all those things are what? Real time signals. And but what is a real signal? If the amplitude of the signal is real, then we call that signal as a real signal. Yeah, it's raining heavily outside. We may lose a signal, but yeah, so hopefully we will not lose. Okay, yes. So next I'll take one more example, like I'll try it here. I take x of t equal to j t. What about this signal? X of t equal to jt. T is what? T is always a real number. That's what we have written here, right? So t is always a real number. So x of t equal to jt is what? Whatever may be the value of t, x of t is always imaginary. So we call this signal as what? This signal as imaginary signal, because amplitude of the signal is always imaginary. So these kind of signals we call them as imaginary signals. Now I take x of t equal to 1 plus jt cube, or let me say uh, t square plus jt cube. What about this signal? It has both real and imaginary parts, and hence we call this signal as what? Complex signal. Okay, we call this signal as complex signal. Okay, so indirectly, what are the amplitudes our signal can take? So our signal x of t can take even complex values, and hence what do we say? We say that x of t can take complex values. Time is always real number. Amplitude of the signal can be real, can be imaginary, can be complex. So in general, we say x of t belongs to C. So this fellow will take care of even real signals and also complex signals. Okay. So typically, the plot of any signal will look like this. Okay. So something like this, right? So this is the way how the plot of signal looks. So note that we can plot the signals whose amplitude are always real. If it is imaginary or if it is complex, we cannot plot. Okay, so because I have plotted the signal here, definitely that signal should be a real signal. Okay, we cannot plot the complex signals, or we cannot plot the imaginary signals. We can plot only real signals. Okay, so what is a continuous time signal here? Continuous time signal is represented as x of t, where t is the independent variable and x is the dependent variable. And what values t can take? T can take any real number. So because it's a continuous time, t can take any real number. But what about the amplitude? Amplitude of the signal can be complex, can be real, or can be imaginary. Okay, yes. And similarly, how do you define a discrete time signal? So discrete time signal, we define it as x of t. Okay, so don't forget the notation. For continuous time case, we write the parenthesis. For discrete time case, we write the square bracket. Okay, so we always use this notation. Okay, at least from now on, let us follow this in your notebook. Also, don't put parenthesis here and don't put square bracket here. Okay, so we make it an habit that for discrete time case we use square bracket, and for continuous time case we use parenthesis. Okay, right. And what are the values n can take? Okay, so just to have the difference, we used two different independent variables. So for continuous time case, what is the independent variable? T. And for discrete time case, what is the independent variable? N. Okay, so and what are the values n can take? N can take only integer values. Okay, that is the difference. For continuous time case, t can take any real number, but for discrete time case, n should take only what? Integers. So that is the difference. Okay, so that I don't want to mention here. Z is the notation. Hopefully you know that. Okay, and what are the values our discrete time signal can take? Correct. So for example, so I can have x of n to be Let us say cos of pi n by 6. What signal is this here? Just compare with the understanding of what we have seen for continuous time case. Here, what values our x of n can take? X of, because it's cos pi n by 6, x of n can take always, x of pi n by 6 is always real, and hence this is an example of what signal? Real signal. Okay, so this is an example of real signal. Similarly, I have x of n equal to j sine pi n by 2. What about this one? This fellow is imaginary signal. Okay, and so on. Similarly, we can have a complex signal also, like let's say x of n equal to e power jn. Correct. So this fellow is a complex signal. So sorry for the clutter, but hopefully you understand that. Okay, so x of n equal to e power jn. So definitely that is a complex signal. So in general, a discrete time amplitude of a discrete time signal also can be complex. So that's what this examples says. So how do you plot these complex, how do you plot these discrete time signals? So here x-axis is n and the corresponding x of n is this. So we use what is called a stem plot. Okay, something like this. Okay, so this is 0, this is as because n can take only integers, even though we draw a continuous line here, but this signal is defined only at integer values of n. Okay, so this is 0, this is -1, -2, and so on. So this is a way how a discrete time signal typically look, and again because I'm plotting, definitely that signal should be what? The signal should be a real signal. Okay, but still we entertain some abuse of the notation, that's okay. So one more way to represent a discrete time signal is like this: x of n equal to something like this. Okay, so we have dot 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 x of 0, x of 1, and dot dot dot. So this is one way of representing discrete time signal. Okay, so we'll use both the representations depending upon the example or depending upon the topic which we are seeing. Okay, yes, so with that we are done with the first classification, which is simple, like what is that? Continuous time. How do you segregate continuous time and discrete time signals? Okay, right. So next, let's move on to the second one, which is even and odd signals. Okay, second classification is even and odd signals. Okay, so when do you say any signal is even yet? So we say that any signal is even. Okay, signal means what? Amplitude, don't forget that. Okay, so when do you say a signal is even? For continuous time case, x of minus t, if it is equal to x of t, then we call that signal as an even signal. So for example, so let us take example x of t, or I'll take x1 of t equal to cos t. This is very typical even signal, correct? So why? X1 of minus t would be equal to how much? Means what? Wherever there is t, replace with minus t. So that should be equal to cos of minus t. But we know the property, trigonometric property of cosine signal. So cos of minus theta is how much? Cos theta. So this is equal to, instead of theta we have t, so we have got what? X1 of minus t equal to cos t. But what is cos t equal to? That is equal to same as x1 of t, and hence what will happen? Cos t is an example of what signal? Even signal. Indirectly what it means, let us plot this signal. Okay, so let us plot cos t and see. We already know that the cos t will look like this. Correct? At 0 its amplitude is 1 and so on. So this is 0. When it will become 0, where it is pi by 2, and at pi this fellow is -1, and again at 3 pi by 2 that fellow is 0, at 2 pi it is 1, and so on. Correct? So what is that you observe here? whatever signal you have from 0 to infinity, the same function will be existing from 0 to minus infinity. So that's what you see. So from 0 to infinity, we have this waveform, and from 0 to minus infinity, it will be just a mirror image of whatever we have from 0 to infinity. So those kind of signals, we call them as what? Even signals. Okay, and we'll take one more example, like x of t is equal to, let us take t square, correct? X of t equal to t square. So how does the plot look? First we will see whether this fellow is even or not. Correct. So x2 of t will take x2 of t equal to t square. So how do you check whether this fellow is even or not? Replace t with minus t. So x2 of minus t is equal to how much? Minus t whole square. And this is same as t square. But t square is nothing but our x2 of t. So what is it we have got? We have got x2 of minus t is same as x2 of t, and hence this is an example of even signal. So let us try to plot this again. Yes, so it's a parabola. You know this, right? So in mathematics, you should have studied. It's a parabola. So this is a function x2 of t. Okay, so because the equation of this curve is t square, so definitely what is that you observe? Whatever we have from 0 to infinity, correct? So from 0 to infinity, whatever we have, same thing we have from 0 to minus infinity, and hence this signal x of t equal to t square is an example of even signal. Okay, right. In that way we can have infinite number of examples. So homework is what? Supply few examples for even signal. Okay, you have to give few examples for even signals. Okay, next. So for this is as far as continuous time case is concerned. So next we will talk about discrete time case. So we'll see that in the next slide. Okay. Okay, so for discrete time case, so what is the condition again? Instead of n, instead of t, we should have minus n. Okay, we have x of minus n should be equal to x of n. So for discrete time case, a signal is said to be even if it satisfies this condition. And what is that? X of minus n should be equal to x of n. Okay, so what is the example? We will take x of n to be. Ah, can you take uh, cos of pi n by 6, which we have seen before, right? Many examples are possible. Let's take x of n to be cos pi n by 6. Okay, so we can easily, we'll take x1 of n. So what will be x1 of minus n? With the same argument we have cos of minus pi n by 6, which is equal to cos pi n by 6, and this is our x1 of n. And because our x1 of minus n is same as x1 of n, definitely it is an even signal. So if you try to plot this function, it looks something like this. So this is our n. So definitely at 0, when n equal to 0, what is the value? We get cos 0. Cos 0 is 1. So it comes like this. Next, when n equal to 1, it is cos pi by 6. Cos 30 is root 3 by 2. So it should be something like this. So this is 0. At 1, it is cos pi by 6. At 2, it would be cos pi by 3, which is half, something like this. At 3, when n equal to 3, what happens? So you get cos pi by 2. Cos pi by 2 is 0. And this continues something like this. And again it falls down and so on. So and same thing repeats on the left hand side, because whatever function we have from 0 to infinity, same thing we should have from 0 to minus 1 to infinity. So minus 1, minus 2, minus 3, and so on. Okay, so this is a cosinusoidal discrete time signal. Okay, so minus 4, oh, sorry, 4, 5, and 6. So at 6, what happens? You will get cos pi. Cos pi value is how much? Minus 1. So at 0, you have 1. At 6, you have minus 1. So you can easily see that whatever we have from 1 to infinity, same thing we will have from minus 1 to infinity. So at 0, we will have 1 as a value. Okay, so in a similar fashion, let us take x2 of n, which is equal to, let's say, mod n. X2 of n equal to mod n. Okay, so let us check whether this fellow is even or not. So how do you do that? You have to find out x2 of minus n. So x2 of minus n is same as what? Wherever there is n, replace with minus n. So you'll get modulus of minus n. What is modulus of minus n? That is same as modulus of n. But what is modulus of n? That is nothing but our x2 of n. So what is it we have got? We have got that x2 of minus n is same as x2 of n, and hence this signal is an example of even signal. Okay, so if you try to plot this, how does the plot look? Yes, at 0 the value is 0. At 1 what happens? That value is 1. At 2 the value is 2, and this continues. So this is 1, 2, and so on. Similarly, at minus 1 what happens? So modulus of minus 1 is again 1. Correct. At minus 2 what happens? Modulus of minus 2 is again 2, and this continues. So what is that you observe? Whatever we have from 1 to infinity, same thing we will have from minus 1 to minus infinity, and hence this function, which is modulus of n, is an example of discrete time even signal or function. Okay, as I said, we can interchangeably use signal or function. Okay, so this is as far as even signals are concerned. So next, let's talk about odd signal. Okay, yes, and again for continuous time case, when do you say a continuous time signal is an odd signal? It should satisfy this property. What is that? X of minus t should be equal to minus x of t. If this condition is satisfied, then we say that particular signal is odd. So note that for very first class, I'll go a little bit slow, and after that we will pick up the pace. Okay. And if you are feeling that I'm going slow or a bit fast, so please let me know, or please Kumaran sir or Satish sir know about that. So I will get the feedback, and accordingly I will change the pace. Okay. Right. But very first class, so please bear with me. I'll go a bit slowly. Yes. So when do we say a signal is odd for continuous time case? If it satisfies this condition, what is that? X of minus t should be equal to minus x of t. Then we say that signal is an odd signal. Okay. What is an example? Default example would be what? Sine t, correct? So just like cos t, we have for continuous time case for even signal. Sine t is a ready example for odd signal. Okay. How do you show that this is an odd signal here? We have to find out again x1 of minus t. So means what? Wherever there is t, replace with minus t. So here also we have t. Let us replace that with minus t. Sine of minus t. But what is sine of minus theta? Sine of minus theta is minus sine t. Okay, here we are using t. In mathematics we'll use theta. So this is same as what? This is same as minus x1 of t, correct? So because sine t is x1 of t, so minus sine t should be minus x1 of t, and hence what do we say? Our signal x1 of t equal to sine t is an example of odd signal. So if you try to plot this signal, how does it look? Yes, so sine t at 0, what is the value? It is 0. Okay, and it goes on like this. This is our sine t. And for negative values of time, it looks something like this. So at 0, it is 0. At pi by 2, that fellow is 1. This should be our pi, 3 pi by 2, 2 pi, and so on. Okay, so this should be 3 pi by 2. Okay, so this so what is that you see? You see that the signal uh, Yes. So if you look at this signal, whatever signal you have from 0 to infinity, the reverse of that signal will be there from 0 to minus infinity. So just look at 0 to pi. Okay, just for understanding. So from 0 to pi, we have a positive oscillation. From 0 to minus pi, what do we have? We have a negative oscillation. Okay, so we call this kind of signals as what? Odd signal. So the same rule applies from 0 to infinity also. From 0 to infinity, whatever we have, the negative of that amplitude will be there from 0 to minus infinity. So we call those kind of signals as what? Odd signals. Okay, we'll take one more example. So let us take x2 of t to be just t. Okay, x2 of t to be t. So how does that look? First we'll check, is it an odd function or not? So definitely we have to look for x2 of minus t. So wherever there is t, we have to replace with minus t. We have t here, replace that with minus t. Okay, right. So but t is same as what? X2 of t. So this is equal to minus, instead of t we can have x2 of t. So what is happening? We got x2 of minus t to be equal to minus x2 of t, and hence this signal is an example of odd signal. Okay, so let us try to plot this. This is t. So when t is positive, it's a straight line passing through origin, right? So when t equal to 0, it is 0, and when t increases, the line also increases. So for negative values of time, the signal or the function goes like this. So equation of this line is what? T. So same rule applies. What is that? Whatever the signal we have from 0 to infinity, the same signal, negative of that signal will exist from 0 to minus infinity. So any signal which satisfies this property, we call that signal as what? Odd signal. Okay, now let's talk about the discrete time case. Okay, same rule applies. I don't want to spend much time here. Okay, so for discrete time case, when do you say a signal is odd? We have x of minus n should be equal to minus x of n. If we have any function of this form, any function which satisfies this condition, we call that as what? Odd signal. Okay, we'll take a simple example. Let us say x1 of n equal to n times mod n. Okay, let us take x1 of n to be n times mod n. Let us check whether this is an odd. We are not plotting this, but yes, let us try to check whether this is an odd function or not. So how do you check that? We have to find out x1 of minus n, and that is equal to, so wherever there is n, you replace with minus n multiplied with modulus of n. Instead of n, we should replace with minus n. So what is that? What is that? Modulus of minus n is same as modulus of n. So this is nothing but minus n times modulus of n. So but we know that n into modulus of n is same as what? X1 of n. So this should be equal to minus x1 of n. So definitely this is an example of an odd function. So I wanted you to plot this signal as a homework. So I'll plot only few samples. Remaining samples you just plot. Okay. So when n equal to 0, what will happen? Because if n equal to 0, this is 0. When n equal to 1, what happens? 1 into modulus of 1 is same as 1. So at 1, it is 1. Okay. At n equal to 2, what happens? 2 times 2, which is equal to 4. So this is 1. So at n equal to 2, we will have 4. At n equal to 3, what happens? At n equal to 3, 3 times modulus of 3, which is 9, and so on. So I'll just put 3 here. Okay, so please supply the samples at -1, -2, and -3. Okay, then you will understand that this is also an odd signals. And what is homework? Homework is supply. Okay, so supply or give, whatever. Supply few examples for discrete time odd signals. Okay, discrete time odd signals. Okay, so in that way we can have odd signals, are we can have an even signal or odd signal depending upon the definition it satisfies. Okay, so next we will talk about what is called even. This is third classification, okay, which is even and odd parts of the signals. Okay, even and odd parts of signal. Okay, even and odd parts of a signal. Okay, so in general what happens, the signals are neither even nor odd, correct? So why should they satisfy those properties? No need. So typically if you give a signal, it can be neither even nor odd, but what happens is that we can get the even and odd parts of the signal. Okay, so we'll write down in general signal is neither even. In general signal is neither even nor odd. Okay, but what happens, we can split. Okay, so we can split it into even and odd parts as follows. Okay, we can split into even and odd parts as follows. So for continuous time case, split means you are splitting. Okay, so we are splitting. So for continuous time case, what happens, we can split our signal. Original signal is x of t, we can split into even part xe of t plus xo of t. Okay, here o stands for odd and e stands for even. Okay, what is that we have done? We are splitting our signal x of t. What is x of t? X of t is neither even, in general, neither even nor odd, but we can split into even and odd parts. Okay, so here we see where xe of t, which is even part, is given by x of t plus x of minus t divided by 2. Okay, and similarly, xo of t is given by x of t minus x of minus t divided by 2. Okay, name itself, one second. Yes, so name itself suggests that it is an even part. So means what? Even part means what? Definitely it should satisfy what property? It should be even. Even part should be even. We'll just look at that. So how do you do that? You substitute t with minus t in even part. So if you replace t with minus t, what do you get? Here also we should replace t with minus t. So you get what? X of minus t plus, here replace t with minus t. So minus of minus t is plus t. You'll get x of t divided by 2. What is this here? This is same as this, right? X of t plus x of minus t by 2. This is also x of t plus x of minus t by 2. So definitely this is xe of t. So what is that we have got? We have got xe of minus t to be equal to xe of t. So definitely what does it mean? The even part is even. So similarly, odd part should be what? Similarly, odd part is odd. You can easily prove that. Okay, I'll put a question mark. You just try to prove that. So means what? Replace t with minus t in xo of t and you have to get minus xo of t. That's easy to prove. So what did we see? We see that any signal x of t can be split into even and odd parts. And even part is given by xe of t equal to x of t plus x of minus t by 2, which is here, and odd part is given by xo of t equal to x of t minus x of t plus x of, sorry, xo of t equal to x of t minus x of minus t by 2. So if you add these two signals, what should happen? xe of t plus xo of t, if you add them, what should we get? We should get back our x of t. That is where we started, right? If you add even part and odd part, we should get back our signal x of t. You can easily see that if you add xe of t and xo of t, what will happen? Right hand sides will get added. So minus x of minus t and plus x of minus t, they get cancelled out. You get 2x of t by 2, which is same as x of t. So if you add even and odd parts, then definitely you will get back the signal x of t. Okay, right. So similarly, same rule applies for discrete time case. Okay, so for a discrete time case, we'll just write down, because same rule applies. We can split x of n as what? X e of n plus x o of n. Okay, where x e of n is given by x of n plus x of minus n by 2, and xo of n is given by x of n minus, same rule. That's why we need not look into the details. Xe of n, sorry, xo of n is x of n minus x of minus n by 2. Again, you can easily see that even part is even and odd part is odd, and if you add these two fellows, you should get back the signal x of n. Okay, right. So we will take a few examples. Before we go into examples, what is that you observe is, if the signal is even, what will happen? If the signal is even, what will happen here? Because it is even, definitely it will not have odd part, and hence the odd part of an even signal is how much? Sorry, 0. Correct. So we'll write down that if the signal is even, okay, if the signal is even, then what happens? Then its even part is what? Is signal itself, and its odd part is how much? Because its signal itself is even, its odd part should be 0. Okay, its odd part is 0. So that is known result, but still we will take down. Similarly, if the signal is odd, what happens? So if the signal is odd, okay, so usually we will write down this. If you use if, then you have to use then. Okay, so if the signal is odd, what will happen? Then the even part, then the even part is how much? Is 0, and odd part is the signal itself. Then the odd part is signal itself. Okay, this is known result, but still we'll write down. Okay, so what does it say? If the signal is even, for example, let us take x of t equal to cos t. What happens? This signal is even. So for this, okay, so we'll take first example like this. So x of t equal to cos t. So for this, what is even part here? Even part is signal itself. Why? Xe of t equal to what? X of t plus x of minus t by 2, according to the definition just now we have seen. So this should be equal to how much? Cos t plus, what is x of minus t? Cos of minus t is again cos t. I'll write down that, divided by 2. So which would be equal to how much? Cos t. And this is how much again? This is our signal x of t. Correct. Cos t is our x of t. So what did we got? We got that if the signal is even, then its even part is the signal itself, and definitely we can show that xo of t equal to 0, means what? Its odd part is 0. So that's what this statement says. Similarly, if you take, let us take x of, even though I'm taking the continuous time case as the example, same rule applies for discrete time case. Okay, so for example, I take x of t equal to t cube. What is this signal at? This is an odd signal. Okay, so for this, what is even part? We will do that. Xe of, so note that this is odd. We know that this is odd. So what should happen to the even part? Even part should be equal to 0. What is even part? X of t plus x of minus t divided by 2. So this should be equal to x of t, which is t cube, x of minus t. So minus t cube is same as minus t cube by 2, which is equal to 0. So that is clear. So what should happen to the odd part? Odd part is how much? X of t minus x of minus t divided by 2. So this is t cube minus of minus t cube divided by 2. So you'll get 2t cube by 2, which is equal to t cube, and this is our signal x of t. So if the signal is odd, its even part is 0 and its odd part is same as the signal. So that is what our previous statement says. Okay, so they are simple, but they will be very useful for us. Okay, so now let us take a few examples in even and odd parts. Okay, find, we'll take that like that. Find even and odd parts of the following signals. Okay, even and odd parts of the following signal. So first example, let us take x of t to be e power j omega naught t, something like this. X of t to be equal to e power j omega naught t. Note that this signal is neither even nor odd, and this is what signal? It's a complex signal because amplitude of the signal is complex. So to find even part, we should know what is x of, to find both even and odd parts, we should know what is x of minus t. So x of minus t would be how much here? E power minus j omega naught. So now let us find out what is even part. Even part is what? X of t. So again, just for understanding, I rewrite the equations, but moving on into the next class, I am not going to write always this equation. You should know them. Okay, so this is equal to e power j omega naught t. And what is x of minus t? That is e power minus j omega naught t whole divided by 2. So this is looking like e power j theta plus e power minus j theta by 2, which is equal to cos theta. And what is theta? It is cos omega naught t. Okay, so similarly, it's an even part. So definitely even part should be even, and that is satisfying that. So what happens to the odd part here? X of t equal to x of t minus x of minus t divided by 2. Okay, I repeat here, I am writing these equations repeatedly, but moving on, we are not going to see these equations directly. I will substitute. Okay, so you get e power j omega naught t minus e power minus j omega naught t by 2. So this should be equal to how much? This is looking like e power j theta minus e power minus j theta. So that should be 2j sine theta by 2 is there, and hence you'll get j sine, that 2 will get cancelled. So you'll get sine j sine omega not t. So clearly, what is odd part? Odd part is imaginary and also it is odd. If you replace t with minus t, you'll get minus j sine omega naught t, and hence odd part of the signal is odd. Okay, even part of the signal is real and it is even. Okay, so and what is it? How do you check whether it is correct or not? If you add even and odd part, so what should we get? We should get back the signal, correct? So this is cos omega naught t plus j sine omega naught t. So Euler's rule, what does it say? Cos theta plus j sine theta should be e power j theta. Theta is how much? Omega naught t. Okay, right. So we will take one more example. Second one. Let us take x of t to be equal to, let's say, 1 plus t square plus t sine t. Okay, so let us take x of t to be 1 plus t square plus t sine t. So, or I will take t mod t sine t. Okay, so 1 plus t square plus mod t sine t. So we have to find out the even and odd part of the signal. So for this kind of signal, there is smart way. So what is that? So if you can easily identify the even parts, okay, if you easily identify, so there are how many terms? There are three terms. So one is there, t square is there, mod t sin t is there. Okay, yes, so definitely you can easily see that one is a dc signal, definitely that is even. T square, just now we have seen that is a parabola, so definitely that is also an even component. And mod t sin t, definitely it is an odd signal. So definitely what happens, we can easily write down what is the even part and what is the odd part. Okay, so for only for this kind of signal. So for previous signal it's not possible, okay, we have to be careful. But for this kind of signals, by what you call that, what you call by inspection, by inspection you can easily find out what is even part and what is odd part. So by inspection, so what would be the even part? So even part, so one should contribute to even part and t square should contribute to odd part. Oh, t square also should contribute to even part. So what should contribute to odd part then? Odd part should be modulus of t multiplied with sin t. Correct? Odd part should be modulus of t sin t. So before we see few more examples, I want to give a small note here. And what is that? Okay, first note, addition of even signals. Okay, so addition of even signals is even. Okay, so addition of even signals is even. So for example, I have cos t and cos 2t. So cos t is an even signal, cos 2t is also even signal. If you add them, the resulting signal is also even. So, okay, so addition of even, no, not only two, multiple signals. So I have three or four even signals. If you add all of them, that still would be an even signal. Okay, so similarly, addition of odd signals, I'm not telling two, multiple odd signals also possible. So addition of odd signals is again odd. Okay, now if you add addition of even and odd signals, for example cos t and sin t. So cos t is an even signal and sin t is an odd signal. If you add them, what happens? It is neither even nor odd. Okay, so addition of even and odd signal. Okay, signals, okay, I will write here is neither even nor odd. That is important. Okay, if you add even signals, you get an even signal. If you add odd signals, you get an odd signal. But if you add an even and odd signal, what will you get? You get a neither even nor odd signal. Be careful. Okay, similarly, what will happen to the product? So multiplication. Okay, so multiplication of even signals. Okay, so multiplication of even signals, what will happen? Cos t multiplied with cos 2t. So definitely what will happen? That is also even signal. So multiplication of even signals is even. I'll try to prove this. Okay, yes, few whatever statements we are given, I have given here. So few of them I'll prove here. Remaining I will give it as homework. So and also multiplication of odd signals. Okay, so multiplication of odd signals Hello. So I lost the signal. So these things were there before.
Yes,
Where
sir.
did we, yeah, yeah, where did we lose here? Uh, just,
Multiplication of odd signals.
okay,
Yes.
so just now we lost here. Okay,
Yes,
that's
sir.
it. Yeah, thanks. Okay, so multiplication of odd signals is even, and we say multiplication. Okay, sorry, multiplication of an even and odd signal is odd. Okay, addition of even and odd signal is what? It is neither even nor odd, but multiplication of odd signals is odd signal. So totally there are 6 statements. So let us try to prove 2 of them. Remaining I will give it as homework. So I have my choice. I'll take the first one and I will take the last one. In between 4, you will take it as homework. Okay, so I'll prove it for continuous time case. Same rule is applicable for discrete time case. Okay, so what is the first statement there? Addition of even signals is even. So let us try to prove that. We'll take only 2 signals. So let us see how it works out. Okay, so we have 2 signals x1 of t. So and we have another signal x2 of t. So these two are even signals. Means what? We have x1 of t same as x1 of minus t, and we have x2 of t same as x2 of minus t. Okay, x1 of t and x2 of t are what? They are even signals, and hence they should satisfy this properties. Okay, so note that I have 2 screens. So camera is from laptop and whatever I write is on the desktop. That's why I see that side. Okay, don't mind for that. Don't mind that. Okay, yes. Okay, so now addition of these 2 signals, let us call that as x3 of t. Okay, so I repeat, we are trying to prove this addition of even signals is even. Okay, so those 2 even signals are x1 and x2, and we what happens if I add these 2 guys? Okay, so addition of those 2 signals, let me call it as what? X3 of t, which is equal to x1 of t plus x2 of t. So what will happen? How do you prove that this is an even? We have to find out what is x3 of minus t. Correct? Wherever there is t, we have to replace with minus t. So what do you get? You get x1 of, we have t here, you get x1 of minus t plus x2 of, we have t here, that should be replaced with minus t. But we know that x1 of t and x2 of t are what? They are even signals, and hence x1 of minus t can be replaced with x1 of t. Okay, so we have x1 of t plus x2 of t. Because they are even signals, we get x1 of t plus x2 of t. Okay, and this is equal to how much? X1 of t plus x2 of t is same as x3 of t. So what is it we have got? We have got that x3 of minus t is same as x3 of t. Means what? That is an even signal. So who is an even signal? X3 of t is an even signal. But what is x3 of t? X3 of t is addition of even signals, and hence what is it we have proved? We have proved that addition of 2 even signals is also an even signal. We can extend it to multiple signals. Okay, so that is as far as first statement is concerned. Okay, yes, and what is the next statement here? Last one. In between we'll take them as homework. Okay, so you please hopefully have written down that. So please try to prove all the stuff. Remaining second, third, fourth and fifth statements you have to prove. Okay, next, last one, multiplication of even and odd signal, we claim that to be odd, so we will try to prove that. Okay, so we have first signal which is even, so that is nothing but x1 of minus t. Correct? And what is the second signal? Second signal is assumed to be odd. Correct? Product of, what is that we are doing? We are trying to prove the multiplication of even signal and odd signal is odd. So first signal is even, and hence we write x1 of t to be equal to x1 of minus t, and x2 of t is odd, so definitely that should be equal to x2 of t should be equal to x2 of minus t. Okay. Yes. So be x1 of t is an even signal and x2 of t is an odd signal. So the product of these two signals, let us again, we can call x3 or x4. So just for clarity, let me call it as x4 of t, which is equal to x1 of t multiplied with x2 of t. Now we want to check whether x4 of t is even or odd. So definitely what should we do? We should replace t with minus t. So to check whether even or odd, we have to replace t with minus t. So if we replace t with minus t, what will happen? We get x1 of minus t because we have t here and multiplied with x2 of minus t. Okay, but what is x1 of minus t here? Because x1 of t is even, x1 of minus t is same as x1 of t, and x2 of minus t is nothing but minus, I'll write down outside, yes, sorry, yeah, it's raining heavily here. Sorry for that. So I'm losing the internet connection. If it doesn't rain, it's good, but yeah, it's raining. Okay, so what is that? I'll stop with this topic so that we don't lose anything. Okay, so what is that we want to prove? We have to prove that product of an even and odd signal is odd. So x1 of t is an even signal, x2 of t is an odd signal. The multiplication is this. Okay, so x4 of minus t, the product of two signals, we assume it to be x4 of t. So we want to check whether x4 of t is even or odd. So what is that we have to do? We have to replace t with minus t and we get this. But x1 of t multiplied with x2 of t is how much? x4 of t. So that should be equal to minus x4 of t. So what is it we have got? We have got that the product of an even and odd signal is an odd signal. Okay. Yes. So I think with that, I will stop for the day. So remaining things will continue in the next class. So if you have any doubts, you can raise your doubts. No problem. If you have no doubts, I will stop for the day. Okay. Okay then. Thanks a lot. We'll meet again tomorrow. Have a good day. So as I said, I am a post-COVID patient, so I'm a little bit tired. My throat is paining, but maybe we will continue the next class. So I'll take some more time in the next class. Okay. Yeah. Thanks. Have a good
Thank you,
day.
sir.
Yeah. Yeah. Good day and good night. Yeah. Bye.
Thank you, sir.
Yes. Yes. Bye.
Thank you, sir.
Yeah, have a good day. Bye.
Thank you, sir.
Thank you, sir.
Sir,
Ah,
class over.
class over. Yeah.
Okay, sir. Thank you, sir.
Yeah. Yeah. You came late or what?
No, sir. My network also got lost, sir.
Oh, okay. Okay. So that's a problem. We will see. Thanks.
Yes, sir.
Yeah. Yeah.
Yeah, thank you,
Sorry.
sir.
Yeah. Good day. Bye.
It's all right.
Okay.